When you are studying curved surfaces, manifolds, structures, and weird shapes, there are many mathematical concepts and disciplines which emerge. And among these, the most predominant is differential geometry and topology. Now, while studying these two subjects, there are certain confusions which I have seen in a student's mind. Why to study, when to study, what are the differences, what are the overlapping factors, do they carry any resemblance, what are the books to study, and how to go ahead and understand. In today's video, we are going to take a kind of a comparative analysis and try to understand what is differential geometry and when it is used, what are the resemblance, what are the differences and other essential factors of these two subjects, differential geometry and topology. By watching this video, you will make your understanding of these two subjects not only clear, but you will very well understand that when these subjects are dealt into, what are the practical usages, which subject comes first, and what are the mathematical preparations that you need to know before you go into this subject. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to a deep dive into a kind of a comparative exploration looking more into these two subjects. Now, as you see that we understand that these two subjects are related to studying the surfaces. And on these surfaces, there are different types of shapes which emerges. As you have already recognized some of these shapes, they are torus, Klein bottle, a sphere, a torus which has got a genus or whole tree, kind of a sphere, a cylinder, and so on. So ultimately what we understand that these disciplines or studying these surfaces requires a kind of a mathematical understanding. So the question is that how do you analyze these shapes? What kind of mathematics you need to study them? What do you get at all after studying these surfaces? What are the new areas of mathematics that are developed, and what are the practical implications that happens when you are studying them? So these are the common questions here. We are going to answer them and we are going to look more into these two subjects of differential geometry and topology. Now we understand that in order to study these surfaces, first of all what we need is calculus. We also need linear algebra, we need partial differential equations, topology, and some part of complex analysis along with abstract algebra. Now there are many other areas like group theory, etc., which I have not mentioned, but I'm trying to give you a basic and a quick understanding that out of all these mathematical tools that we need in order to study surfaces, we will concentrate on this and this, that is calculus and topology. And the reason will soon become very clear. So when we talk of the first one, which is calculus, which is highlighted in red, we come to what is known as differential geometry, and then you will understand that why we are using the word calculus. Now when we talk of differential geometry, it comprises of two words, differential, which obviously comes from the concept of calculus, which is called differentiation, where we are understanding the infinitesimal small differences using calculus, and we are applying the rules of calculus. When you're talking of geometry, that means we are talking of structures, surfaces, where all the physics and the mathematics takes place. And using calculus means that we are not using any flat Euclidean space, but the entire underlying structure or entire physics or whatever we call as the dynamics which takes place. So what we can tell from this is differential geometry is a branch of mathematics that focuses primarily on the study of geometric shapes, and it uses predominantly differential calculus as a tool. So it uses derivatives, local analysis, tangent spaces, and different other areas which are connections to differential equations. So as I highlighted calculus right in the box, so it becomes clear that why we are using calculus, and that actually leads to the understanding of the subject differential geometry. Now if you can look into the picture, you see that here if I draw certain lines technically called geodesics, this would converge leading to a positive curvature. In this part of the structure, it will go on parallelly infinitely, it would lead to zero curvature, and this would a kind of a diverge which will lead to negative curvature. So if we try to plot all of those on a kind of a surface, then what we do is that we divide the surface into very, very, very small, infinitesimal small pieces, and we apply the rules of calculus. So if you are willing to calculate what is called the differential area, then we can use dy by dx and we can calculate that. So applying the rules of calculus on these surfaces which are called technically manifold, and as you can see that these yellow boxes, they looks like an ordinary piece of a Euclidean space if you zoom and further zoom onto the surface. So I'm not going into the details of the technicalities of what is a manifold, which I have covered a lot in my other videos on differential geometry, which you can take it out in my channel Physics for Students. So what we can see is that dividing a surface into infinitesimal small pieces leads to calculus. Now we come to the next question. We have understood overall from here that what is differential geometry. Now we come to the next part, that what is topology. Now the word topology is actually taken from this word which means place or location, and topo means place and logy means actually study. So you can say it is basically a kind of a local place and study on the subject. So we can say the topology actually is the study of property of spaces which does not change if they are distorted, warped or twisted. Now herein comes the big difference and our first understanding of differential geometry and topology. So we can say that topology actually studies properties of spaces that do not change or technically invariant under continuous deformation. A study that is concerned with size and shapes which remains same when they are distorted. Obviously there is an advantage that why we are saying that the shape won't change and would be invariant. We will look into that, but this is what topology is concerned about, that we will make certain changes but it would be invariant under continuous deformation. So we can say again from the definition that topology is the area of mathematics that describes properties of object that remains unchanged. So from here let us look into this. A circle is equivalent to a square which will be equivalent to a rectangle, and we can say that a circle is topologically equivalent to a square which is equivalent to a rectangle. And from here we can say that we have to remember that geometrically they are different. Obviously, because a circle's radius and a square has got an angle. So geometrically, although they are different, but topologically they are the same. And from here, we can say that whatever the property is there in the circle, it will be same around here and it will be same around here. That means, as I told you, that if you deform them, it would be still the same. So if you go back to the definition, you will see that the properties of the objects remain the same, although I would say they are allowed to bend, twist and warp and do something. So one property bent will be equal to the same as the second property and equal to the third property. And this is tremendous, and this would lead to great implication in terms of understanding of physics and mathematics. So as you see here that I can say a torus and a coffee cup and a ball, all of them can be twisted and turned into a circle and a square or a rectangle or any kind of a deformed shape. Now, if you're really wondering that how this can be done, I would request you go to my playlist on topology. You will see there is a very long lecture where I have used clay muds, colored clays, and I have actually shown on the camera that how these can be twisted and turned, and they can be turned into any kind of a shape. And again, from this shape, you can, that is from a rectangle and a square, you can go back to a cup and a ball. So that is basically called the function and the inverse of the function. So we can say from here a circle is topologically equivalent to a square which is equivalent to a rectangle. So all of this can be turned into here. And we should remember that they are geometrically different. So all these shapes from here, we can say that if I take all those shapes and I deform, stretch or bend, then what we are trying to achieve is a metric free system. That means there should not be any metric, Euclidean or non-Euclidean or ellipse or nothing. It will be a metric free system or a distance free system where the measurements will be invariant. So here comes the use that why do we need topology? Because topology lets us talk about the notion of closeness, which in turn allows us to talk about concepts like continuity, convergence, compactness and connected without the notion of distance. So topology generalizes fundamental concepts of analysis or calculus. Now you might ask me a question that why do we want a metric free system? Because the moment we get a metric oriented system, we are confined to a shape, to an angle, to a particular system. And as in physics we are going for a theory of everything, in topology it is also the same, that we are looking for a much more bigger generalization, where a cup can be equal to a circle, that circle can become a square, it can become a rectangle or whatsoever. But the concept is that there should not be any notion of distance, because the moment we get a distance, we are bound to a metric system. So as you can see, this circle, this cube, and then all those shapes, these are Euclidean shapes, rectangle, square, and then this triangle. When they get generalized into this kind of a shape like torus or sphere or a Klein bottle or anything, then what we can say is that we are moving from Euclidean to non-Euclidean. We are moving from specific shapes to irregular shapes. We are moving from Euclidean axioms to topological axioms, and from a metric system to a much broader system, which is called a topological space. I have got a separate video which you can look into my playlist if you want to know what is a topological space, because it is something very technical. So we are again generalizing. So topology, now you can understand the kind of a difference or relation between differential geometry, is something which is much more broader in sense. So the next questions comes that what is the purpose? What is the purpose of learning those things? Coming up into the next part of the video, we are going to explain the purpose. So if I take two sides, differential geometry and topology, I can say that the main purpose of differential geometry is to understand the geometric properties of spaces and shapes in a precise way, and which leads to obviously physics, general relativity, computer graphics, etc. Now look into the definition of topology. Topology is not always about understanding. Definitely it is about understanding, but it is to classify spaces based on their intrinsic properties, which remain unchanged under continuous deformations. That means, for example, if I take a group of elephants, and if I study the structure of certain elephants, and if I deform those elephants to create another shape, and if I know those elephants will have A, B, C, D properties, then I know that by deforming or getting a similar kind of elephant, we will get all those A, B, C properties. And that becomes extremely handy and useful for physics and other purpose, because one structure leads to the another structure, but by just knowing those properties of one structure, which might lead to a deformation, which might lead to a bend, but the basic structure will remain the same. So the marked difference in differential geometry is that it is basically to analyze and study. Topology is mostly related to classification and categorization. So in topology, as you can see with those who know, that there are different classes, categorization of shapes, genus 1, genus 2, genus 3, and so on, and many other things. Why do we do that? Because we want to categorize them and use the mathematics so that one category might be equivalent to other without even going into the details of that category, because we already know the characteristics of that particular category. So we come to the next question, that we understood what is topology and what is differential geometry. What are the differences? How it makes these two things different? So I will take to one part, that is the aspect, and if I say the focus on differential geometry is basically smooth structures and properties of surfaces. Topology's focus is basically on a global area, including qualitative properties like connectedness, holes, genus, etc. Differential geometry primarily tends with local area. That is why when studying general relativity, we study differential geometry, because gravity is a local manifestation of space-time, and in topology it is primarily concerned with global, and that is why the complexities are more. If I say the tools used, very simple, you just need to know calculus, differential equations, and tensors, but here a lot of homotopy, homology, and algebraic tools are being used. If I talk of curvature, the central concept, both of them are the same, but it is how surfaces are bent. But in topology, we are concerned with curvature, focuses on continuous deformations. I'm sorry that I cannot show you what is a deformation in this scope of the video, but if you go to my videos on topology, you will understand what is homeomorphism and many other concepts. The next thing is that it accounts into what is called smoothness. And differential geometry primarily requires what is called a smooth or differentiable surface, and topology really doesn't work because it is much broader, so it can actually work with any continuous surface. Differential geometry particularly deals with geodesics, which topology doesn't, and the objects which are studied in differential geometry are Riemannian manifolds, curvature, and connections, and this is related to topological spaces, which are quite technical to explain, not surfaces and manifolds. The main theorems of differential geometry are Gauss-Bonnet theorem, Riemannian geometry, and in topology it is classification theorem, fundamental group theory, and so on. The applications are mostly on physics, stress analysis, etc. Topology is much more abstract, sometimes on quantum field theory or condensed matter physics. So the basic viewpoint is differential geometry is more on measurement and metrics. Topology is more qualitative, that is shape and continuity, and we want to get out of the matrix system. Intrinsic versus extrinsic can study both intrinsic and extrinsic, but primarily concerned with intrinsic properties. Relation to calculus, yes, differential geometry uses a lot of calculus, but topology is less on calculus, more on algebraic concepts and set theory. Now, we know the differences, but are there certain similarities also? Well, knowing the similarities also gives you a better connection with the subjects, and once you know, then you get a better picture. So what are the similarities between differential geometry and topology? Let us look into the next part of the video. So both of them study manifold, remember, but differential geometry, it uses differentiable structure, but topology does not need to be a differentiable structure because it is more global, more generalized. Both of them deals with geometric objects, both differential geometry and topology. And the surface classification, yes, the classifies surfaces based on smooth and structure, but this is more related to topological invariance like Euler characteristic. But you see that both of them studies manifold, both of them uses geometric objects, and they use surface classification. What else? Yes, they have got a connection and curvature. Differential geometry uses Levi-Civita connections, etc., and this is more onto the topological concept. Mathematical structures, it is using tensors and differential geometry. This is using algebraic structures, and this has got an application in physics. This also have got an application in physics, but much more on an abstract scale. So you might now have a question that which one is easier to learn. Now it is difficult that somebody finds topology to be easy, somebody finds differential geometry to be easy. So that is why I have written that some find topology more intuitive because it is abstract, etc. But what I can tell is that if you talk of differential geometry overall, then I can tell you that differential geometry is actually more concrete and visual in nature. It becomes very easy. The familiarity in terms of mathematical foundations are very easy because all of you know different, calculus, linear algebra, real analysis, etc. Local versus global, it is much more local, so it is easy to start, and it is less abstract for initial learning, and there are a lot of intuitive examples and analogies which the textbooks actually provide. So I think that that it is much easier in order to start learning. Now, if I talk of topology as a whole, I mean to say which one is easier. First of all, it is more abstract and visually intuitive because topology introduces new and abstract concepts such as open set, compactness, etc. Topology concerns itself with global properties of space such as whether the space is connected or compacted. Topology typically concerns itself with global properties, which makes things a little bit complex. Highly abstract in nature because in its very basic form it introduces concept like for example, the notion of a topological space itself can be quite, I would say, foreign to students accustomed. And some of the examples like Mobius strip, Klein bottle, they are very, I mean to say, when I started visualizing what is called a orientable, non-orientable surfaces, it becomes very difficult, because they are very counterintuitive and challenge the conventional notions. So understanding these objects required a kind of, I would say, shift in thinking that can be difficult for students. So overall, I can say differential geometry seems to be much easier. Now here is one point which I have not mentioned, but I would like to tell. Some of the books of differential geometry assumes that you know topology. I have actually shown that in my earlier videos how to learn differential geometry, which you can check in. So please take a note, be aware that if you're purchasing a book on differential geometry, if it assumes that you know topology, and you should check that whether you at all know topology or not. If it is not, discard that book and assume a book which doesn't assume that you know topology. So from here what we can say is this one, that differential geometry particularly focuses on smoothness, curvature and local coordinates, and it considers I would say local properties like curvature to affect the global shape and structure. Considering the topology, it is mostly on local connectedness using abstract tools to understand, and it investigates global properties which are connectedness, compactness, and topological invariance. So this is what we can say overall what these two subjects they really demand. So now finally let us look into the mathematical prerequisites, which will finally give you a complete understanding that how difficult or how complex they are. Differential geometry, obviously you need to know calculus, the ordinary partial and ordinary differential and the partial differential equations, a good understanding of linear algebra, multivariable differential equations, real analysis, basic geometry, and basic topological concepts. That's the last one you can just ignore. As I told you, certain books in differential geometry do not assume that you know topology, so you can very well go ahead with those books. Topology, although the list is less in number, it works primarily on set theory, abstract algebra. You need to know a lot of real analysis, especially what is called a proof-driven mathematical system, elementary topology that you need to know, a lot of algebraic topology and homology and homotopy. So homology and homotopy actually gives a part of the algebraic part. So number of, I would say topics which are required to learn topology are less. Differential geometry are much more, but these are very abstract, very advanced. So from here it again proves the fact that you learn differential geometry first and then move into topology. So that's all for today's video. This is a quick snapshot in going a little bit deep into understanding these two subjects. Thank you very much for watching this video. If you've liked, please do subscribe and click on the bell icon to get all the notification from Physics for Students. You can write to me at this email ID, and you can also subscribe to my other channel, General Theory of Relativity. You can follow me on my Facebook, LinkedIn, Instagram, and Twitter account. Physics for Students will be soon back with many more interesting videos, but till then, goodbye.